Okay, let's get started. It's the end of semester where there's like 10 people here. I love it. Okay, thanks for showing up. Okay, so last time we talked about DNSSEC. That was probably the last like major protocol you're going to see all semester, where we spend a whole lecture walking you through how it works. But I find it really cool. The idea is that we take DNS and then we add the security on top, but we had to make it backwards compatible. The two big ideas were first, we're going to use signatures to cryptographically verify records. So the name server signs it offline, and then everyone else uses the public key to verify. And then the second idea was that we somehow like inserted the idea of certificates by introducing this hierarchy, where we use the domain hierarchy so that every name server can not only tell you where the next name server is, but also endorse the next name server by signing their public key. And we talked about how you would implement all of this in like total full detail by talking about the new record types, DNS key for the public keys, the DS and RR-SIG pair of records that allow me to delegate trust to someone else, and then the RR-SIG to sign my final answers. And then finally, we briefly mentioned, you're not going to get tested on it in like too much detail, the idea that in real life, every name server actually gets split in two. And so the upper half uses its key signing key to sign the lower half's public key, which is the zone signing key. And then the lower half can sign records for all the future name servers. And then finally, we talked about how if a record doesn't exist, we actually have to be a little bit careful. And so we had to design NSEC to say, if a record doesn't exist, you need to be able to sign a message saying there are no records in this range of domain names. And if you don't like that, you think that leaks domain names, you can upgrade to NSEC 3, which actually hashes the domain names before alphabetizing them. But those are kind of the high-level ideas behind DNSSEC and its design. All good? Anything else you want to know? That's DNSSEC on one slide. Okay. So today we get to start kind of the end of the class, like the home stretch. Most of the lectures from here on out are just kind of like special side topics. So we're not going to talk about a whole protocol front to back, but we're going to talk about things that are still really important. Like, don't get me wrong, we could probably teach a whole class on either of these topics, but we're just going to give you the high level overview. And then, if you're interested, you can go explore more. Okay, so that's the end of the class. It's kind of a survey of all the stuff that we wish we had time for, but didn't have time for. And so here we are going through them. Okay, so the first thing, and it's really important, but it's something that we haven't really talked about in detail yet, is denial of service. And again, this could like fill a whole class, but today I'll use this to fill half a lecture. Okay, so this is one of those properties that we've mentioned a couple of times, but we haven't really dived into. And so it's the property of availability, which is if I have a service that I want users to be able to access, I would like them to be able to access it. And the denial of service attack attacks availability by trying to make this website or this service unavailable for the people who really want to use it. And well, there's like tons of reasons why you might want to do this. So maybe you want to do it. It's kind of like the same as all the reasons from lecture one. So you could do it for profit. You could do it because it's like a rival company you don't like. You could just do it for a political statement. You could do it for censorship because you want to just have fun, all sorts of different reasons. But these are all attacks on availability. And the idea is that I don't want legitimate users to be able to access someone else's service. So I'm attacking the service itself. And this happens like all over the place. I can probably like go online and find all sorts of different articles. Here's one from, I don't know, what is that, 12 years ago? But it basically shows that you can like pay for DOS services. So one option is to make someone else do it for you. That's like, security is economics or something. Here's one from, I guess, 2005, but it still happens. So there could be like extortions, or somehow someone like takes your website down and says, give me all of your secrets or else the website's going to stay down, or like pay me this amount of money or else your website's going to stay down. So there's like all sorts of stuff you can do. This stuff comes up over and over again. I'm sure like you've seen it in the news too, if you follow that kind of stuff. So today we're going to talk about how you would execute these attacks, and then maybe ways to defend against it. And we'll see a couple of like really specific examples just to illustrate why these are dangerous. Okay, so to me, there's kind of two categories of a denial of service attack. So the first category is the program that's running the service is somehow broken. So I'm going to somehow force that program to like crash. And if the program crashes, then nobody can access it. So this could be something like maybe the program is written in C and there's some buffer overflow and you can use it to like shut down the program or just like crash the program and now it can't run. Maybe there's some like SQL injection vulnerability and you like delete the entire database So these are flaws in the program itself. The program itself has some way for the attacker to cause the program to stop working or shut down. And so that's one possible way you can attack a program or a service. And then the other way you can attack is called resource exhaustion, or that's what I've called it, which is the idea that everything has like limited resources. So there's no such thing as infinite resources. And so whatever limit there is, whether it's like computation or network bandwidth, I can somehow overwhelm that. And if I'm using all the resources and the computer like runs out of memory or is no longer able to send any more packets because it's like sending as many packets as it possibly can already, then maybe legitimate users are going to time out or somehow error when they try to visit the website. So one idea is we can crash the program that's running. The other idea is we can somehow overwhelm the program so it runs out of resources. So those are kind of two possible categories, like attack vectors. And so we'll look at them both. So in both cases, or I guess maybe in the second case in particular, there's this idea of a bottleneck, which we'll see a couple times today. And the idea is that maybe your program has a bunch of different moving parts. So maybe it's not just a single program running. Maybe you've got like a database, and you've also got the program itself, and then you have all these other side programs that are doing other things. So your system could be really complicated. And so, maybe someone will try to do denial of service on all the different parts. But really, a lot of programs have something called a bottleneck, which is, maybe you've heard the term before in even non-CS contexts. But the idea is that the bottleneck is the place where the resource limit is the tightest. So this is the place where it's easiest to overwhelm because the resource limit is small. And if I overwhelm the bottleneck, and that could cause the whole program to go down, well, then maybe that's a place where the attacker wants to target. So maybe an idea you've seen before, maybe one we'll see today. Okay, so we talked about two different ways we can attack something. We can attack the program and crash it, or we can overwhelm the resources by trying to target some bottleneck. And then there's another kind of axis along which we can make decisions. And so this axis says, well, what layer are you actually targeting? So when we run a program, we know it runs on all these different layers. We've seen the whole networking stack before. So we could target the very highest layer and target the application itself. So this would be like targeting the program itself that's running, targeting the resources on my computer that's running the program. So that would be like application level. But then we could also maybe target the network itself and somehow target one of those lower levels to overwhelm the like network protocol. So I can make a choice here, decide between application or network, the layer that I'm attacking at. And then I can also independently make a choice between, am I going to try to overwhelm the number of resources that are available, or am I going to try to somehow crash the protocol or crash the program by exploiting some flaw? So those are all choices that you get to make if you're trying to figure out what these attacks are, how to defend against them, and hopefully not how to execute them, but I guess we'll show you some approaches here. Okay. So I'll start with the application level. And so here I want to target the resources on the application. So this is like the computer running the program or the program itself. And this is different for any program that I'm running. But something that a lot of these attacks have in common is the idea of like asymmetry. And so the idea is that if I'm trying to overwhelm the amount of resources, well, maybe the attacker doesn't have access to a ton of resources. So how are you going to attack the server if you don't have a lot of resources yourself? You're going to have to look for places where there's asymmetry, where the attacker only has to spend a little bit of resources, but they can cause the server itself to consume a lot of resources. So this is an attack that's cheap for the attacker to implement, but super expensive for the target. That's the kind of thing we're looking for. There could be other attacks out there that are maybe more symmetrical, where the attacker has to pay a ton, and then the server wastes a ton of resources. So those might be more symmetrical, but those would be more expensive for the attacker. So the attacker likes the ones that are asymmetric. The attacker pays a little bit, but the server consumes a lot. So there are a lot of different examples of this. So here are some examples of programs that we don't want the actual server to execute. I haven't told you like how you'd make the server execute stuff like this, but you can imagine there are programs that like exhaust the file system space. So these are examples of resources that are limited. So every computer, I don't know about you, but like my computer has a limited amount of space on it. So if I just start writing a bunch of garbage to the file system, maybe that will exhaust the amount of space on my disk. I could also exhaust the amount of memory. So every computer only has a certain amount of like working RAM memory. So if I try to malloc something massive, that could like maybe crash the program or cause the program to run out of memory. Every program, if you've taken like an operating systems class, maybe there's a limit to the amount of threads that you can run at a single time in parallel. So maybe I can like try to exhaust that, start a bunch of different processes. A lot of disks also have like limits on how many things you can read and write at a given time. So maybe I'll try to like open like 1,000,000 files at once, or try to like write to all these different places. And maybe that will also cause the disk to complain. So these are all just like high level ideas of how you might, or like what you might want to do as part of an attack. Although I haven't said like how you would do these, we can imagine those are all ideas that are out there. Okay. Here's one that I find really cool, and I find even cooler. Does anyone know, like, I got roped into Teach 61B this semester, which is our data structures class. So I got to see merge sort and quick sort in like way more detail than I ever wanted to remember. But okay, so this slide has like special meaning to me now, I guess, but it's still really cool, especially if you've taken a class like that. And so maybe you remember, I just spent like 2 lectures proving to a bunch of like little kids or freshmen or whatever, that merge sort is n log n in expected runtime and worst case. So in other words, no matter what you throw at merge sort, it always runs at n log n time. And I finally like remember what the proof of that was. You don't have to for this class, but I had to. So I'm telling you that. Okay. And then you might remember there's another algorithm called quicksort, which also sorts a collection of items. And this one, if you give it a random set of inputs, it's n log n expected runtime. However, if you give quicksort a specific array, and does anyone even remember which one it is? It's a sorted array, then quicksort takes n squared time to finish. Or if you give it an array that's like sorted but backwards, it's still n squared time. So in other words, merge sort is n log n no matter what you throw at it. Quicksort is n log n with overwhelming probability on random arrays, but it is n squared if you choose a really bad array. And so the idea is that, well, if somehow like someone's running like a sorting service, I don't know why they would, but maybe they're running a sorting service and they allow users to input whatever things they want. Well, maybe an attacker who's trying to exhaust the amount of resources, they could like intentionally give the sorting service an array that's already sorted, or an array that's sorted but backwards. And that would cause quicksort to run in n squared time. So this way, I'm causing the server to run and use even more resources by giving it a specially chosen input that I know causes worst case runtime on certain algorithms. So that's a really cool attack. From 61B, you don't have to know this, but like I was looking it up and I found out that apparently, depending on your implementation of quicksort, you can actually come up with specially designed arrays that cause n squared runtime. So even if you use like different variants of quicksort, there are still algorithms out there that apparently like specifically target quicksort by giving it worst case arrays. And there's like a whole field of theory out there if you're curious. But the takeaway is that if you have a problem like this, you're trying to put out a sorting service to the world, and you want to choose the sorting algorithm that is safest, then maybe there's an argument that merge sort is safer, because no matter what you throw at it, it's never going to run in really slow n squared runtime. It's always a safer n log n. So even though maybe like in practice, you might prefer quicksort because it's faster on average, maybe in the case where you're worried about attacks, maybe merge sort is the one you want to go with. So it's an open question, depends on what service you're running. That's the idea behind the algorithmic complexity attack, supplying inputs that cause the worst case runtime, which could be really bad, and maybe use up a bunch of resources or use up a bunch of time. Okay, pretty cool. So those are just kind of some ideas, right, behind maybe ways that you could implement denial of service attacks. So now let's talk about ways you might defend against them. So, well, one thing you should do is you need to somehow figure out that you're being attacked. So that's actually easier said than done, and we'll see this again throughout today. But first, you have to figure out that someone is trying to exhaust your resources. And that might not be totally obvious. Maybe the request looks legitimate, but then you start getting more and more and more, and you're like, wait a minute, this doesn't look so legitimate after all. And so somehow you have to even figure out that someone's trying to attack you. And how might you do that? Well, it's not super obvious. Maybe somehow you want to force every user to like log in before they ask you to perform some service. And then maybe if a single user keeps like spamming you with requests, you're like, wait a minute, that user is trying to do something nasty and trying to like cause me to exhaust all my resources. So maybe somehow you have to like tell everyone to authenticate themselves and then try to figure out which users are being bad and which users aren't. Maybe that's the thing you want to do. But even then, you have to be careful with denial of service attacks. The authentication service itself, maybe some user tries to, or some attacker tries to spam a bunch of login requests, and now you're spending all this time performing hashes or something. Maybe that's also going to cause you to exhaust resources. So you have to be super careful, because any part of your program that you allow users to interact with could be vulnerable to something like this. Other ways you could defend against this are you could try to use ideas of like isolation or quotas. And basically the idea is that you don't want one user's actions to affect other users' actions. So if one user is spamming you with requests, that should not cause you to make your entire service go down and suddenly other users can't even use your program. So maybe somehow you like separate the service out so that different users are using different parts of your service. Maybe that's something you can do depending on what you're building. Another idea is that maybe you can only give every user a certain amount of resources, and maybe that's limited. So you can say, okay, today for, if I'm building a sorting service, today you can sort, 10,000 things. And that's all that I'm allowing you to sort, and there's no more. And so maybe that's one way to stop people from overwhelming your system. You give everyone a limited amount of resources that they can consume like per day or per hour. And once they use that all up, no more for them. Something else you could do is maybe you could say only users that are trusted. So maybe they have to like sign in or they have to have a verified email or something. And only those users that you trust can execute requests that are expensive and everyone else cannot. So those are all ideas that you could take with you if you're trying to defend against these attacks. Okay, there's more. So something else you could do is you could maybe make the user spend some resources before asking you to do something. And so here we're going to try to make those asymmetric attacks a little bit less asymmetric. So in general, there could be attacks that exploit asymmetry where the attacker pays just a little bit and is like, hey, please generate 10,000 random numbers. And then now you are stuck here like generating a bunch of random numbers and wasting a bunch of effort. But maybe you can make the attacker's life harder. So instead of just having the attacker say, 10,000 random numbers, go, and then you have to do a bunch of work, you could maybe ask the attacker to do something expensive as well. So maybe the attacker has to now solve a CAPTCHA, which we know either takes time or money. Maybe the attacker has to somehow like do a certain amount of work before you do the work. So now the attacker has a harder time forcing you to do a bunch of work. So that's a possibility. People call it proof of work. And then there's also another solution which always works, but it's kind of silly, which is what if you just have a gigantic amount of resources? So if I just somehow pay for like infinite compute, then an attacker can no longer overwhelm my resources. So why not just do that all the time? Well, because it costs money. So if you want to have a gigantic amount of resources, that's going to cost you money. And maybe that money is not worth it if you're not that concerned about DOS attacks. So you have to think about your threat model. What kind of people are going to be attacking you? Is it worth paying for like, billions of gigabytes of storage if you're just worried about very rare attacks or if there are no attacks at all? So it depends on your threat model. And maybe if there's something you really care about, then maybe this is something that you want to do. So for really big services out there, like, I don't know, Google or something, maybe they do over provision because they care about going down quite a bit. I don't know. I don't work for Google, so you'd have to ask them. Okay. Quick final note on this slide is sometimes if you don't want to over provision, because that's going to cost you a lot of money, you can use something called a content delivery network, which I find really cool. And so the idea is kind of like insurance. Does everyone know how insurance works? Everyone good at like being adults and thinking about insurance. So the idea behind insurance is that we all pay a little bit of money and it goes into a pool that the insurance company collects. And then if one of us, I don't know, like suffer some sort of accident, like knock on wood, we don't, but if one of us gets into some accident that's super expensive, well, then the insurance company is going to take that pool and then like use it to help whoever got into the accident, help them out, right? Or help them recover whatever they lost. And so the idea is that we all pay a little bit to minimize our risk. It goes into a pool, and then whoever gets unlucky, they get the pool that was collected. And so that's the idea behind insurance. So the idea behind a content delivery network is kind of the same. Every one of us that has a website, we all pitch in just a little bit of like money or resources. And then it goes into this big pool that's managed by some company, like Cloudflare does this for people. And then the idea is that if someone tries to attack, then we take that big pool of resources that we've all teamed up to create, and then we allocate all those resources toward whoever's getting attacked to try and help them out. So it's kind of like an insurance scheme. Everyone tries to minimize their risk by paying just a little bit, but because there's a lot of us, we all team up and we get a lot of resources together. And then that big pool of resources can be like dynamically allocated toward whoever needs it. So that's pretty cool. Okay, if you're interested, I'm sure Cloudflare has like a blog or something you can read, but that's all you have to know for this class at least. Okay, that's it for things that are happening at the application level where I'm overwhelming the resources on a computer itself. or the server itself. Anything you want to know before I talk about the network level? So now we're going to talk about networking protocols, how to break those. Anything on Zoom? No? Okay. Time for some network level attacks. So now instead of attacking the program itself, which is what I've been doing so far, like maybe the program itself was sorting and I give it a bad input. Well, now instead I'm going to start attacking the network itself. So I'm going to think about the protocols at the lower layers and think about how do I attack those so that the victim or whoever it is that I'm trying to attack is somehow like going to now struggle to like access the internet. Can I do that? So there's a bunch of different ways I can do this as well. So you could think about trying to overwhelm the victim's amount of resources. And when we say resources, we have to be a little bit more specific. So we could say, well, maybe the victim only has a certain amount of bandwidth. So it's like, maybe I can only download this much of, or this amount of data per second, or maybe I can upload this amount of data per second. So if I spam the victim with a ton of like upload and download requests, maybe the victim's going to run out of bandwidth and now is no longer able to upload or download requests from other users. That's a possibility. Or maybe somehow the victim's networking protocol has a certain limit to the amount of packets it can process. So maybe as the IP packets like start flying in, the victim's computer is only able to process like 10 per second or whatever limit. And so in this case, maybe if you send it a lot of really small packets, you can cause it to like log jam, get a traffic jam, and now it's unable to process all the packets in time. And then when the legitimate packets come in, now they're stuck waiting as well, or they get dropped. That would be bad. Okay. Maybe when you think about denial of service and you see it on the news or whatever, you don't see like DOS, but you see DDoS, you see that extra letter in the front. So like, what does it stand for? So it stands for distributed denial of service. And so here the idea is that it's not just one attacker trying to overwhelm the victim, it's multiple attackers or one attacker with multiple systems, all trying to target the same victim. So this will be the picture of a denial of service attack that's like distributed. So you have a lot of different people all attacking the same service. And so this one is really powerful. And this is why you see this in the news all the time. So why is this so dangerous? Well, this one's really dangerous because if an attacker has a bunch of systems at their disposal, well, first of all, now the attacker is super powerful because they have access to all these different computers and machines that can all attack the victim at once. So maybe in this case, the attacker has the advantage. They've got a lot of bandwidth. And then something else that's really hard now for the victim is now there's like spam data coming from all over the place. So maybe it's not like before where there's just a single person sending you a bunch of requests and maybe you just tell them like, okay, no more for you. And then everything is good. But in this case, the spam or the overwhelming packets are coming from all different directions. They're coming from everywhere. And so now the victim has a really hard time telling, is this packet good? Or is this packet coming from one of the like 10 different attackers? And that's a lot harder to tell who's an attacker and who's not. So this makes it really hard for someone to defend against it. And so one thing you might ask is, how the heck is an attacker going to get this many systems under their control? And well, there's lots of different ways for that too. So maybe they like pay to get a bunch of systems under their control if they have the kind of money for that. Something else they could do is maybe they have some sort of attack that they can execute on like a bunch of different computers. And then all of the computers are part of their control. So they have this big army of computers that they've compromised using the same attack. And then the attacker can be like, okay, like army of computers, like attack. And then they all like start sending packets to the same victim. Sometimes people call that a botnet, where all the computers have fallen under the attacker's control. Now the attacker can tell the entire army to start flooding a single victim. So those are ideas behind DDoS. And the reason why it's so dangerous and so hard to defend against is because traffic is now coming from all different places and not just one place. Okay. So more kind of potpourri and about denial of service. You can see this lecture is kind of just showing you a bunch of different ideas that are helpful and maybe not like diving too much into any specific one. So before we talked about asymmetry. And so we said, well, it would be really nice if the attacker just had to spend a little bit of money or a little bit of resources and then cause the victim to have to spend a ton of resources. So an example of this would be like, I'm not going to do this, but you can imagine some like, really evil instructor could be like, okay, all of you, your homework is to like go home and start like copying the dictionary or something like that. So how much work does that take for me? Like not much. I just have to tell you to do it. But then how much work does it take for you? Like a ton, because now you're at home copying the dictionary. Don't actually go home and copy the dictionary. But that's an example of asymmetry or amplification. So here's another example that actually uses one of the protocols that we've seen, which I find kind of cool. And so the example from here is called DNS amplification. And so the idea is that, like, think about the DNS protocol. When I send a response, or when I send a request, how big is that request? It's pretty small. It has just a single record that says, what's the IP address corresponding to this domain name? So it's really small. It's a tiny request. But then do you remember those responses that came back? Were they bigger? Well, yeah, they were a lot bigger because they said things like, oh, here's the next name server, and here's like 13 different, NS records, and here's 27 different A records. So you might remember those responses tended to be a lot bigger, just in terms of amount of data, number of records, compared to the requests. So could I somehow use this to attack someone? Well, there is one thing we could do, which is I know that the request is really small. So to send a request takes me no effort at all. But then the DNS name server sends a really big response in response. And so somehow this DNS name server is like an amplifier. It takes in just a little bit of data, but returns a ton of data. So it's amplifying the request, and you don't have to be the person to do the amplification because the DNS name server is doing it for you. So, well, what can I do with this? Well, if I don't have the DNS name server amplifier at my disposal, I would just have to send a bunch of packets to the victim. And that means that it's totally symmetric. So every extra packet I send is an extra packet that the victim receives. Or like if I send 10 bytes, the victim receives 10 bytes. There's no asymmetry. Everything I pay is the same thing as the victim pays. But if I could leverage this amplification from the DNS name server, maybe I can somehow send, as the attacker, send like 10 bytes, but then cause the victim to have to receive like 1,000 bytes. That would be amplifying my response. So how do I do it? How do I get the DNS name server to send a really big amount of data to the victim without me having to consume a big amount of data myself? So the idea is to spoof. So if you look at this packet is spoofed because it's really coming from the attacker, but the attacker is lying and saying it's from the victim. And so it goes to the server. And how big is this packet? It's really tiny. It's just a small little request. The DNS name server gets this packet and says, oh, I got a question. Time to answer it. And so who is the DNS name server going to send the answer to? This is the whole idea behind spoofing, right? Does it go back to the attacker? No, because the attacker lied about where it came from. This response that is spoofed is going to the victim instead. The victim never asked the DNS name server a question, but they're still getting this gigantic response because of this spoofed request. So the attacker sends a request, it's really small, and it's spoofed, and then the DNS name server sends a response that's massive, 27 records, another 13 records, all of it goes to the victim. So here we're exploiting asymmetry to amplify the power of our attack. It's pretty cool. Okay, questions about this one? This is one of like 2 schemes you'll actually see based on actual networking protocols today. Okay, so that's pretty cool. So what are some good things about why you might, or why an attacker might do this? Like, what are the advantages? Well, we already saw one of them, which is the attacker pays just a little bit, like sends 1 record, but then the victim receives like 27 records in response. So the attacker is able to amplify the attack. And you can also imagine that a DNS name server probably has a ton of capacity because it's out there answering these questions all day. So sometimes you can take advantage of these servers out there that not only amplify, but also have tons of capacity. And so you can make them do all the heavy lifting and make them send all the garbage data and garbage packets to the victim so that you don't have to do it yourself. And the other kind of benefit that you get from this is now the attacker, well, the victim, I guess, doesn't really know who the attacker is. Because like, look at the packet the victim receives. It says from server to victim. And I look at this and I'm like, wait, who's attacking me? Is the name server attacking me? Well, not really. The attacker was doing it. But the victim, according to this diagram at least, has no idea who the attacker is. So in some cases, you can even hide who the attacker is. For example, when you do the DNS spoofing attack. But I suppose it depends on the specific attack. But sometimes you can conceal who the attacker is because the packets look like they're coming from the amplification server, even though the attacker was the one who initiated all the attacks. Okay, so why not just do this all the time? Why don't attackers just always do this all the time? Well, one problem is that you have to be able to spoof. We know it's possible in theory, but maybe some networks block spoof packets. So you have to be a little bit careful. For example, if you're an off-path attacker, then TCP spoofing is hard. That's something we already saw. So you have to be able to do the spoofing. Here we were using UDP, so it wasn't too bad. But you can imagine that if I was doing TCP, then spoofing is a lot harder because I have to get that entire handshake right. And that's like from the TCP lecture. Okay. Amplification, pretty cool. So now let's talk about how you would defend against network level attacks. So one possible idea is, because these are happening over the networking layer, and I have all these packets streaming in, and I have to figure out which ones are good and which ones are bad. Well, maybe I need to somehow come up with some sort of filter that says, these packets are good, these packets are not. And so I have to design this thing. And how would I design it? Like, what would the filter do? And that's kind of a difficult question. And we'll see why it's so difficult probably in a couple slides. But somehow I want this filter that tells me these packets are good. They come from real users. That packet is from an attacker trying to do a DOS attack. So I'm going to reject this packet, but accept this packet. But how do I know which packets are from legitimate users and which ones are from the attackers? Turns out that's not so easy sometimes. And the other problem is that the packet filter itself could be the bottleneck. So what if the packet filter is doing something super expensive to check if a packet is good or not? And then I flood a bunch of packets and the packet filter itself like craps out or just runs out of memory. Well, now the packet filter itself is also vulnerable. So somehow this defense that I added to stop DOS attacks, the defense itself could be DOS. So you have to be really careful. Everything has limited resources. And so you have to be careful. Okay, I realize I said you have to be careful twice, but it's true. Okay, other things you can do to subvert packet filters as the attacker. So how might the attacker try to get around this packet filter? Well, one thing you could do is you could try to spoof packets. So even if I'm not doing any sort of amplification attack, I'm just sending a bunch of packets, I could still spoof them and lie about where they're coming from. And now the packet filter has a harder time telling which packets are good and which packets are bad, because all the bad packets are coming from all these random IPs. So that could be harder to defend against. Another idea is if you use distributed denial of service or DDoS, in this case, you don't have to spoof and lie about where it's coming from because the packets are actually coming from all these different places. So even if you don't lie about where the packets are coming from, they're still coming from all different places. And now the packet filter has to be really smart to figure out which packets are good and which packets are part of a denial of service attack. So it's pretty tricky. Okay. As before, there's still a defense that always works at the application level, at the network level, at every level, and it's just over provisioned. So just go out and buy a ton of equipment so that no one will ever have the bandwidth to overwhelm your network. And again, why would you not always do this? Because money, it costs money. And maybe your threat model says it's not worth it to pay all this money, but it's a possible option out there. Or you can use a content delivery network like Cloudflare, and we can all play insurance and like pay a little bit and then have someone else over provision. But that's always a defense that's out there. Okay. So those are all kind of high level ideas behind denial of service, why it works, approaches that people would take, defenses that people might use. So I'll show you just one example that's like really hammered out and like it's a full protocol, or not protocol, yes, but a full attack on a protocol, just to give you a flavor of what these attacks are like. So here I'm going to try to exploit TCP. And so the idea is, remember this TCP handshake? It's a three-way handshake. The attacker sends a SYN, the server sends a SYN-ACK, the attacker sends an ACK. Okay, it's all good stuff. We've seen it before. And so you can also imagine this thing is super common. Everyone uses TCP all the time. And you can also imagine that when this TCP handshake gets completed, or like when it's starting up, the server needs to allocate some memory. If it's like running in some program, it's got to allocate a little bit of memory so that it can store things. Like the server needs to remember, wait, what was the sequence number that the attacker gave? Also, what sequence number am I choosing so I can start counting out myself? Maybe I have to store some memory to keep track of data that's like streaming in, but hasn't been processed by the user yet. And so there's a lot of stuff that the server has to remember as soon as this TCP connection starts running. So every TCP connection has to have some amount of memory allocated to it so that the TCP connection can use that memory to write down things that it cares about, like sequence numbers, or like, hey, this piece of data just came in and the user hasn't requested it yet, so I'm going to hold it here for now, stuff like that. And so the idea is that what if the attacker forced the server to start like 20 different TCP connections, 100 different connections, 1,000,000 connections? Well, now the server has to remember the sequence numbers for 1,000,000 different TCP connections, and that could be a lot of data to remember. Maybe the server runs out of memory before it finishes remembering all the stuff from all these different connections. So that's the idea behind overflowing or overwhelming TCP. But this seems kind of symmetric because for every connection that the server remembers, you're like, wait a minute, doesn't the attacker also have to start up that connection? So if you want to make the server remember 1,000,000 TCP connections, doesn't the attacker also have to start 1,000,000 connections? Isn't that really expensive for the attacker too? Like, where's the asymmetry? So here's where the attacker is going to make this attack possible and more practical by exploiting asymmetry. So the idea is, if I look at this handshake, who goes first? The attacker is the one that goes first. And then when the server receives the response, the server is the first one to remember data. So if I look at this picture, the attacker says, I want to connect, here's my sequence number. And immediately upon receiving the SYN, the server's got to say, okay, I got a sequence number, time to write it down, time to generate my own sequence number and write that down too. So as soon as the attacker sends a SYN packet, the server is now obligated to remember a bunch of stuff. Even though the handshake hasn't finished yet, the server right here after the first step is forced to like allocate some memory. Okay, so how's the attacker going to exploit that? Well, the attacker knows that none of these connections are ever going to be legit. So why does the attacker ever have to remember these numbers? Well, maybe the attacker doesn't. So what if the attacker just sends the SYN? Now the server is sitting there like, okay, I got to allocate some memory, and then I'll reply with the SYN ACK. What if the attacker just never acts? These connections don't have to actually finish, because by the time we get to this step right here, the server's already allocated the memory, send it the SYN ACK, and is like, okay, I've got this space all ready for your brand new TCP connection. I'm waiting for you to reply. And well, the attacker doesn't have to reply. The server might just be sitting there with all this memory. And if this happens over and over again, then the server gets totally overwhelmed. So the reason why it's called SYN flooding is because the attacker sends nothing but SYN packets over and over again, forcing the server to think, oh shoot, I'm so popular, like 1,000,000 people want to connect with me and start connections. The server has to start and allocate a bunch of different memory spaces for each of these different connections. But the attacker knows in reality, none of those are ever finishing. So the server has to allocate all that space, but the attacker who knows none of these connections are ever finishing can just send a SYN and then forget about it right away. So the attacker spends a little bit of space, right? Just sends the SYN packets, doesn't have to remember anything, but then the server is totally overwhelmed, has to remember all the different connections. Okay, that's SYN flooding. It's pretty cool. Okay, how would you stop this? Okay, as usual, there's always the same defense over and over, which is I will simply have enough space for 1,000,000 connections. If you think that's the defense you want to do, it is out there. But again, cost, threat model, all that good stuff. Another possible idea is, what if I somehow do some filtering? Like, can I somehow like say this TCP connection is legitimate and this one's not? But like, that's kind of tricky because if I look at this connection has a total of 1 packet. And what does the packet contain? A sequence number. So if I show you a packet with a sequence number and I ask you, is this a real user or is this an attacker? What are you going to say? I don't know. It's kind of tricky to tell because there's no data in here. How do I know if this is an attacker sending me garbage or a real user trying to connect? I don't know because all I have is a single SYN packet. So you could definitely try to filter, but filtering will be pretty tricky because it's so early in the connection that you don't have any sort of signal as to like, is this a good connection? Is this a bad connection? So it's kind of tricky. And again, all the same problems from before apply. Someone could overwhelm the filter. The attacker could spoof the addresses so that the filter has a hard time telling who's legitimate and who's not. All those same problems apply. But there is a defense that is specially targeted towards SYN flooding. It's called SYN cookies. And so the idea here is, I don't know why they call them cookies now that I think about it. I guess you can think about it as we're going to send a little bit of state back to the attacker, if you want to think of it that way, in the same way that cookies store state by sending things back and forth. But basically, the idea is that the server is going to kind of say, okay, well, you made me go first and allocate memory, but actually, I'm not going to do that. I'm going to make you allocate memory first. So the attacker is going to kind of like reverse it and make the attacker go first. And if I make the attacker go first, then now the asymmetry that makes this attack possible is going to be totally gone. So here's what it looks like. Here's like a conceptual picture, and then we'll make it real, I guess, in one more slide. Okay, so we already know that before, the client would send this into the server, and at this moment in time, the server is obligated to allocate a bunch of memory because the server has to prepare for the connection to finish. So in other words, the server is going first. But what if the server didn't go first? What would that even look like? So at this point, the server is obligated to remember a bunch of stuff, and that costs memory. But what if the server said, actually, I don't want to go first. I'm going to make you go first. What would that look like? Well, what if the server says, I'm not going first. I'm going to send all that stuff back to you. So whatever stuff the server had to remember, whether it was like configuration information or sequence numbers or ACK numbers, the server is going to say, I'm not storing that. I'm going to send it back to you, the client, in the SYN-ACK. And then the client, if you really intend to finish, if you're not just SYN flooding me and you really want to finish this connection, then you should send that stuff back to me instead. So in other words, I'm forcing the client to go first. And at this point, the client's going to have to start up and store all the state. And only then is the client going to send the state back to the server. And then at this point, the server is ready to actually allocate state because the handshake is done and the connection is ready to start up. So all that I've done is I've taken the state that would have otherwise been stored here at this first step, and I fired it back at the client. And I said, I'm not writing this stuff down. Like, you write it down and send it back to me. And then the client sends it back. And only at this point is the server happy, saying, okay, this connection is probably real. So at this point, I'm going to start and write all this stuff down, allocate the memory. And so now the idea behind asymmetry is gone, because what happens if you flood a bunch of SYNs over and over again? The server just says, I got a SYN. I'm not going to allocate memory. The stuff that it would have allocated, I'll send it back to you and you remember it. And so the server never actually allocates any memory until this final step is done. So now SYN flooding doesn't work. If you still want to overwhelm the attacker, you actually need to also create a bunch of connections yourself. And so now it's going to become more expensive for the attacker, and the whole asymmetry is gone. Okay, that's a SYN cookie. That's the nice version of it. But of course, I cannot go in and modify TCP for the same reasons that DNS had to be backwards compatible. I cannot go into TCP and say, oh, there's suddenly a new state. Can't do that. That's going to break all of TCP. So where do I put this new state? I have all this stuff I want to remember. Like, where does it go? So here's what people actually do. Here's the SYN packet. And instead of sending back some extra state that I can't just like add into TCP because there's no place to put it, I'm going to put it in the sequence number. That's kind of cool. So the idea is that instead of coming up with any random old sequence number, I'm going to somehow take that stuff that I really wanted to remember and put it inside the sequence number. We know the sequence number is just a bunch of ones and zeros, and usually they're chosen at random, but who said those sequence numbers can't represent some extra stuff that I care about? Maybe they can. So somehow in those ones and zeros, you can encode the information that you care about, and then where's the extra arrow? The client can send it back to you, and then you can look at the ACK number, extract the information that you care about. So that's what people might do in real life. Okay, so this is basically the same as before, by the way. The only difference is that instead of having this magical new state that appears out of nowhere, I instead have to put the state inside the sequence number. And we know that's okay because the sequence number has this like 32-bit series of ones and zeros. I could use it to represent some information if I felt like it. So that's what the server does here. Okay, so why is this so useful? Well, the reason, again, why this is useful is because the attacker now has to be the first one to, they have to go first. They have to store memory and allocate memory first. And the server is not going to just store memory or allocate memory on every SYN. It's going to wait for the whole handshake to finish. Okay. I think that's mostly it for SYN cookies. It's the one attack you have to know for today. Anything you would like to know about it? It's probably the most complicated part of today as well. So anything else you want to know? Okay. Kind of cool. I like it. Okay. End of first part. So it's your last chance to ask DOS questions at all. Otherwise, I'll talk about firewalls for the last 35 minutes, and then we'll be done. Okay, cool. Let's talk about firewalls. It's kind of a separate topic. So even if you fell asleep during DOS, it's okay. This is a different topic. We'll start from scratch. So what are firewalls? Why do I care about them? And so the reason why I would care about them, here's like the setting that I'm going to use, and then we'll talk about how you might build something. So the setting is you are somebody managing a company. Like, it's a really big company, and you would like to protect the company against external attacks. So there could be all these different people who want to attack your company, and you would like to stop everyone from the outside from attacking your company. And so why is this so hard? You're like, well, that's not so bad, right? I'll just go around, protect all the computers. But why is that so hard? Well, one problem is that how do you know how many computers are there? Like, or there could be like hundreds of computers in your big company. Some of the computers could be really old and outdated. Maybe they don't have good security. Maybe some computers are operated by people who just aren't security aware. They don't have the right software. They are going around clicking on malicious links all day, right? Like, how do I protect all of these different people? They have different hardware, they have different software, the operating systems could be different. Some computers could be so old that you're not able to update them. There could even be computers that you just don't know about that are in this network. So I have this huge, gigantic local network of all these computers, and I want to stop them from being attacked from the outside. So how do I do that? I could go around trying to secure every single machine, or I could somehow try to scale or make this scalable and secure the entire network with one system. So that's my new goal, which is I'm not going to go around securing every little service one by one. I would like to secure the whole network one at once. So this is what it's going to look like. So there's the firewall. I guess this is also, I don't know if this is super relevant anymore, but like back when I did this a couple of years ago, I would always tell people, like, this is one of those points where people always like to, this is by the way, super off topic, but people always like to compare, like CS topics to real world and be like, oh, this is just like real life, whatever. And while I think it's like true sometimes, I don't think it's always true. And this is one of those cases where I don't think it's true. So I do not endorse this, but the solution that we're going to use to secure the entire network is we're going to like build a wall. Okay, like very 2016 of me to say that, but we're going to build this wall, and it's going to be a great wall, and it's going to stop everyone from the outside from attacking the services inside. I do not endorse this in real life, but that's what we're going to do. Okay, and so the idea is that there's going to be a single point of access, and so all the machines from outside, like the entire rest of the world, if they would like to access or talk to the people inside the network, they have to go through this single checkpoint, right? There's this absolute wall, and everyone has to go through the single checkpoint in order to access or send packets inside the network. And that single checkpoint, we're going to call it the firewall. And this actually is relevant, or you can think of the security principle like complete mediation, right? The idea is that there could be all these different ways to get into the network, but I'm going to enforce that every single person has to talk to the firewall first if they want to enter my network. And that way I can check who's an attacker and who's not. Okay. And this is going to protect the entire network. Remember that like in this local network, if they want to talk to the rest of the world, they also have to pass through the firewall first. So everyone is mediated through the firewall. And so this structure works just fine. And the only question left to answer is, what does the firewall do? Right? The firewall is sitting there. It's some program that you're not going to have to write. And the program is specifically going to have to say, I just received this input from outside, or someone from inside wants to send this packet. And the firewall just has to judge and say, is this allowed? Do I let it pass? Or is this not allowed? Do I not let it pass? And do I block it? And so the last thing I have to implement to make this firewall totally work is I need to write the code sitting inside the firewall. What does it allow? What does it not allow? And this depends on your threat model. So if you think that anything goes, the firewall could just be like, yep, everyone goes through. If you want to be super paranoid, you could say, oh, nothing goes through. In reality, you'd probably want something in between. And so you'd have to come up with your threat model and figure out like, what is a good threat model? What attacks am I trying to stop? Who's trustworthy? Who's not? In particular, one thing that we already assumed when we built this threat model is we assumed that everybody inside is trustworthy and everyone outside is not. That's why we want everything from the outside to go through this checkpoint, because we think all these people inside, they're all trusted. I don't want anything from the outside. That's an attack. So the firewall is going to check everything from the outside. So we've already kind of thought about a threat model, but if you have different threat models, you could certainly design the firewall differently. Anyway, that's the structure we're going with. So now let's think about what policies could I use? There's actually lots of different ones out there, so you can pick whichever one you want. Here's an example of one that you might choose. So maybe the firewall says, what do I do with packets that are on their way out? They're coming from the inside and they're going to the rest of the world. You could do whatever you want here. You could like say, oh, I'm going to like flip a coin and deny it half the time. It'd be very strange, but you could. But one policy that people sometimes use is if it's outgoing, I'm just going to allow it. Because what did I say in my threat model? My threat model says everyone on this side of the firewall inside the network is trusted. So if something is going outbound, it's coming from the inside, going through the firewall, it's probably coming from someone I trust. So I'm just going to let it go. If it came from inside, it's trustworthy. I'm going to let it go. If you don't like that, you think some of these people are malicious, you can change your threat model. But a common threat model out there is that everyone inside is trustworthy, so outbound traffic is okay. Okay, that means also that anyone inside can connect to any service. So you can connect to any website you feel like. And if you don't like it, change your policy. Okay, what about inbound? Well, what about the packets coming in this way? Now you have to distinguish what's good, what's bad, what is allowed, what's not. And so now you have to pick some rules. So here's a possible set of rules that you might consider, which is I'm only going to allow inbound messages if they are a reply to something that was outbound. So like if someone inside sent a letter to someone outside and then someone outside sent a reply, I'm going to say that's okay. It's a reply to someone that I trust. So I'm going to assume that's okay. Maybe there are some services that you're okay with. So maybe like if the connection is run over SSH, you're going to allow it. It's kind of up to you. And then maybe you could say everything else is not okay. So if someone outside wants to talk to someone inside unprompted, you might say, nope, can't do that. I'm only accepting replies to conversations that were initiated from the inside. That's a possible approach. Again, this is just an example. So if you don't like it, you can write different rules here, but it's pretty like open-ended. So you can put whatever you want there. Okay, so maybe allow outbound, maybe only allow some inbound, and maybe deny everything else. Okay. And so, well, again, there's kind of a problem here, which is that when I'm writing this code, in all likelihood, you are not going to write literally every single rule that covers like any possible request. There's just too many possible packets out there. How are you going to write a rule for every single packet, including ones that you've never seen before? So most likely, your rules are going to miss stuff. So what happens if one of the packets that comes in like doesn't check off any of your rules? Do you allow it? Do you deny it? You're probably going to have to default to something. So you can either write your policy as default allow, which basically says everything is good except for this. So you're listing out the things that are not allowed. Everything else is good. And so that's called default allow. And that's called you writing a deny list. So you could do that. And another option is you could do default deny. So in this case, you specify these are good. Everything else is not good. So whichever one you like, you can use. Which one do you prefer? Depends on your priorities. So if you are concerned about users being able to use software, maybe you want to do default allow, because if there's a piece of software you've never seen before and the user wants to use it, it would be nice to allow it by default so the user can use it, as opposed to default deny, where you're going to be like, I've never seen this before. I'm going to deny it by default. And now the user is angry at you. So default allow is better for usability, but it could be dangerous because what if the thing you've never seen before is an attack? Well, then now you're in trouble. So default allow is more flexible, but more dangerous. By contrast, if you really care about security, maybe you prefer default deny. I'm really paranoid. Everything could be an attack. I want to be super careful. So I'm going to deny everything except for the stuff that I know for sure is trustworthy on my allow list. So that would be more conservative, but it's worse for usability because what if you miss something? It's going to get default denied, and then the user is going to complain at you, and you have to slowly build the list of stuff that you trust, which could be more work. So if you're paranoid, you care about security, default deny is probably better. But if you care about usability, maybe default allow is better. So it's an open question. You can go with whichever you prefer. Okay. So that's the firewall. That's how you might write some rules. Something else you could think about what the firewall is doing as a rule is you could think of the firewall as a packet filter. We kind of saw this in the DOS unit as well. And the idea is that what does the packet filter do? It takes a packet and has to answer yes or no. Do I allow this packet to go through, or do I block this packet and drop it right here and disallow it? So you have to make a choice. For every packet that comes in, you need to analyze it and make a choice. So the simplest kind of filter you could possibly make is a stateless filter. And here the idea is that you're just going to look at every packet individually. So you're not going to think about the packet that came like 5 minutes ago, or you're not going to like think about packets that could hypothetically come in the future. You're going to say, there's one packet in front of me right now. I'm going to look at just that packet and nothing else. That's called stateless because you're not remembering state. And so that means that the only thing you can use to judge if the packet is good or not is the packet itself. You can't think about things in the past. Don't think about things in the future. Just look at the packet itself and make a decision. What's nice about this is it's simple. What's bad about this is that it might miss some attacks. So how might you like implement something like this? or how much you implement one of our policies from earlier using a stateless packet filter. So one thing you could do is, if you're using TCP, right, how can I tell if something is a reply or not? Well, I remember that if I'm replying to something, there's probably an ACK flag set. So if I see the ACK flag set on a TCP packet, I could say, well, I'm just gonna look at this packet all by itself. It has the ACK flag set. So I'm gonna say this packet is probably good. The ACK flag is set. It's probably in a response to something else. That's one possible kind of hacky way to implement this policy. Maybe if the ACK flag is not set, like if someone on the outside is trying to connect to the inside, what would they send? They would send a SYN packet with no ACK flag. You would see that and say, nope, I'm not allowing inbound connections that are brand new. So I see that there's a SYN flag, there's no ACK flag. I will deny this. So that's a possibility. With UDP, it's a little bit harder because UDP doesn't have the notion of ACK. So how you would implement this is kind of an open question, or maybe a bit trickier. Maybe it depends on the specific UDP connection protocol, but that's one possible way you can implement a protocol like this using a stateless filter. So again, you can do whatever you want. You can like say, oh, I'm gonna only accept packets with this flag and this flag, but that's possible, or that's one possible idea. Okay. What if you don't like that? What if you think stateless is too weak and you want stronger protection? Well, this is where stateful packet filters comes in. And so here, the idea is that I'm going to keep state, which means that not only am I going to look at every packet one by one, but I'm also going to remember packets in the past that have come before. And so that means that instead of looking at every packet one by one, that's like the packet mindset, I'm going to start thinking about like the connections. Because if I have a bunch of packets, I can reassemble them into a connection, and I can start keeping track of like data that the other person sent, or data that the user from the inside sent to the outbound, or data that's inbound from the other person. So I can keep track of connections now. And then I can think not only about every packet one by one, but think about the different connections. Okay, I'm going to sit down because I got kind of lazy. Anyway, so ultimately, you still have to make the same decision, which is you get a packet, it's either good or it's not good. But instead of just looking at every packet one by one, you get to think about the packets in terms of connections, which is kind of cool. Okay, so here's an example of a connection rule that you might allow. So you might say, now that I'm keeping track of all the different connections, I'm going to allow connections that come from this IP address to this IP address, but only if the destination port is 80. So that's something you could say. Something else you could say is you could say, oh, I'm going to allow everything, right? The star is like a wildcard character for any IP address. So I'm going to allow connections from anybody as long as they're from inside the network. And I'm going to allow those connections to go to anybody outside, but only if the outside port is 80. So you could allow that too. I could say, I'm going to allow everything that's outbound. I could say, I'm going to allow anything that's incoming, but only if it goes to this particular IP address. So maybe inside your server, you have all these different computers. Some of them are top secret, but one of them is serving a service to the outside world, and it has this IP address and this port. Well, then maybe you say, anybody coming in is not good, except for this particular inbound connection. So if they're trying to connect to this server, it's okay. If they're trying to connect to any other server, it's not okay. So you don't have to like memorize the syntax, but I find it like reasonably readable. Basically, the stars for a wildcard, INT for internal, EXT for external. That's all you got to know. Okay. Rules, firewall rules, all good? Okay. And again, the reason why you're able to do this is because the filters are stateful now. So you can keep track of connections and remember, oh, this packet came from this connection, so it's good. Or this packet came from this connection, so it's bad. Okay. What else do I need to tell you about? Stateful packet filters, they can be smarter. So instead of looking at every packet one by one, you can reassemble packets in TCP, like use the sequence numbers to reassemble. If you're using something like HTTP, you can be even smarter and reassemble that too and be like, oh, that's a GET request and that's a POST request. And maybe like, I'll accept POST requests, but I won't allow GET requests. So stateful packet filters can be a lot smarter if you would like to. It would just be more expensive to implement, but it's a possible trade-off you can make. Okay. FTP is a file transfer protocol. I'm not going to talk about it, but if you're curious, there it is. Okay, so this part I find kind of fun. It's an example. It's a little bit contrived, but it demonstrates how people can subvert packet filters. So how might an attacker try to get around the packet filter? So let's say this is my policy, right? There's all different policies out there that you could implement. I'm going to choose to implement the policy of if the message that is incoming contains the string root, I'm going to deny it. I'm going to think this person is trying to log in as the administrative user who is called root. I'm going to deny that. So if I ever see a packet that has ROOT in that order, I will deny. It's no good. Everything else, it's okay. Everything else is good. So for example, let's be the stateless packet filter and let's look at these one by one. So I look at this one. Do I let it go? Yep, because I look through the letters. There's no root. I look through this one. Looks good. There's no root. I look through this one. Uh-oh, problem. This one says the letter root. No good. So I drop this packet. I keep the other two and I let them go. Okay. So how might I subvert this? Because if I look at this, it seems like if someone wants to type in the word root, then they're going to get caught because I'm going to find it. But remember TCP, I can split messages across different packets and reassemble them. So what if I do something like this, where I send one packet with the letter O, one packet with the letter R, and then O, and then T. And what does the firewall do? It looks at each of these one by one and it says, well, this one says O, that's not root. That one says R, that's not root, not root, not root. So all four of these actually go through the firewall, and the firewall lets them through. And then what about the person on the other side? Well, now the person on the other side is going to reassemble these using the sequence numbers, and they're going to get the word root. And that's bad. We don't want that. So that could be one way to subvert, is to split the letters across different packets. Something else you could do is you could send them out of order. So maybe this firewall, it got a little bit smart. It's like, actually, even across different packets, if I see ROOT, I'm going to stop and deny it. But maybe the way you can get around that is you can send them out of order. So I could say, I'll send the O first and then the R. So I'll swap the order of those two. And now the firewall gets even more confused because it says, well, that spells OROT. That's not root. So maybe the firewall lets these packets go. But then on the other side, when they reassemble using the sequence numbers, they do get root. 4, 5, 6, 7, that's root. Okay. So how would you stop this attack? Well, now the firewall has to be smarter. The packet filter not only has to have state and remember all these different packets, but the packet filter also has to be able to reconstruct the connections. So this packet filter went from just being stateless and just checking characters one by one to now having to understand the TCP protocol and understand how to piece together packets using sequence numbers. So this firewall had to get considerably smarter just to stop this attack. Okay, are we good? If the firewall speaks TCP, does that mean everything is good? But here's an even stranger attack. And so this attack exploits the fact that IP packets have a time to live. And so what that means is that, do you remember how packets take a hop or a bunch of different hops to get to its destination? Well, what if a packet gets like lost, starts going down the wrong path, or maybe a packet gets trapped in a loop somewhere and gets sent like back and forth, or the packet just somehow like wanders off path and goes in the wrong direction? Well, we don't want those packets to be stuck in the network forever. So even though we didn't mention it explicitly before, IP packets do have a time to live, which basically says this packet is only valid for this many more hops before it's going to say it's out of hops. Now it's probably just stuck somewhere. It's gone off the wrong path. I'm just going to drop this packet and they can resend it if they're using TCP. So every time the packet takes an extra hop, we take the time to live and decrease it by 1 to say you have one less time step left to live, one less time step, one less time step. Oh, you're out of time. This packet gets dropped, and this avoids having packets like bounce around the internet forever. Okay, so how do I exploit this? Well, maybe the firewall and the end host, the person you're actually trying to talk to, maybe they live at different distances away from you. So maybe I'm the attacker, I'm on this left side. Maybe the firewall is like, I don't know, 10 hops away from me in the nearest route. But then the end host is another couple of extra hops away, 13, 14 hops, whatever. And so maybe what I could do is, well, first I have to figure out how far the firewall is and how far the end host is. And the way that I could do that is I could maybe see how long does it take for the firewall to respond to me? How long does it take for the end host to respond to me, and see how, see how long they take. I could also send packets with increasing TTLs to see if they reach the firewall. So for example, I could send a packet with TTL 10, see if it comes back. If it does, it means it reached the firewall. If it never came back, the firewall is probably more than 10 hops away. So that's something you could do. But basically the idea is I can figure out how far away anybody is, and then I can exploit the TTLs to do something like this. And I can say, I'm going to send all this crap. Some of it even has duplicate sequence numbers. Who knows? Maybe they're corrupted packets. I don't know. But the firewall can look at all of these And even if the firewall was super smart and knew how to reconstruct TCP packets, if you're the firewall and you get all this stuff, what message is being sent? Because you have two values with sequence 4. You don't know which one is right. You've got 2 with sequence 5, 2 with sequence 6 and 7. You receive all 8 of these packets and you're like, what's the answer? Is it like roots, like what is the answer here, right? And what message is being sent? The firewall doesn't know. But maybe because of the way that I set these time to lives, some of these packets have a shorter time to live and they just like fall off and stop existing before they reach the end host. And it turns out of these 8 packets, only 4 of them arrive at their destination. And you can guess which 4, ROOT. So now the firewall could not see the right answer because the firewall lives earlier in the network, or like earlier in this sequence of network hops than the end host. So the firewall sitting here is kind of confused, but then the end host still gets root. That could be possible. So this is really tricky to defend against because these time to lives can be different. So I can't just look at these and be like, oh, this one's short, oh, this one's long, because I don't really know what path the packet took to get here. I don't really know if it's going to get to its destination because the numbers can vary now and then. So it's kind of tricky. Like, how do I know which of these are going to get there? I don't really know. How do I know what the actual message is? Am I going to have to try like every possible combinatoric number of like, oh, well, the first one could be an N and an R. Second one could be like O and an I, so it'd be like NOOT, like newt, I don't know, or like RICE, rice, maybe, I don't know. There could be all these different messages. Do I have to like check them all? That could be really expensive. Now maybe I'm opening myself up to denial of service. So it's really tricky. Okay, so all of these examples are just to show that there are ways to subvert these packet filters in like increasingly complicated ways. And if this firewall isn't like really smart, it can get fooled in ways like this. Okay, and you also have to be careful because if the firewall gets too smart and starts computing things really complicated, that are really complicated, well, now maybe the firewall itself could be vulnerable to denial of service. So it's a really difficult trade-off. Okay, there are some other types of firewalls. So if you don't like this, you're like looking at these packets one by one, and now I have to speak TCP and stuff. This is just too hard. So there's other types of firewalls out there. They're called proxy firewalls. And so here the idea is like, forget looking at every packet one by one. This firewall is going to say, if you want to talk to someone inside, you can't talk to them because they're on the inside. So instead, if you're on the outside and you want to talk to somebody, you're going to talk to me, the firewall. And then I am going to form a separate connection to forward your message to the server. So now the firewall is acting as a middleman. It's saying, if you want to talk to someone inside, you can't do that. Talk to me first. Like I'm the agent, like it's like talk to my agent, right? The firewall is the agent. And we form a connection with the firewall, not with the server inside. So now the firewall is not like trying to look at every packet one by one. The firewall is the real intended destination. And the firewall can look at the messages and then decide whether or not to forward them to the server on the inside. So you can either think of it as the firewall is the middleman, and I'm forcing everyone outside or inside to make separate connections to the firewall, and the firewall is going to forward the packet instead of people on the inside and outside directly connecting. Another way to think of it is the firewall is just a full man in the middle. So we're giving them man in the middle capabilities to edit or drop or read any packet that you get. You can also do this at even higher layers. So if you want to do this at a higher layer than TCP, you could say outside, if you want to talk to someone, like don't talk to me, talk to the firewall, create a brand new HTTP connection, talk to the firewall. If the firewall thinks it's okay, the firewall will form a new HTTP connection on the inside and then forward your messages. So that's the idea behind a proxy. We will probably see this again in a little bit, but that's the high level idea. Okay. What if you don't like firewalls, or how do you get around firewalls? So one thing you could do is you can use a virtual private network. So I'm sure we've all used this before to like pretend we're in other countries and like watch, I don't know, like whatever, like foreign Netflix or whatever. I don't know what people use this for anymore, but basically, what does this even do? Like, why does this allow me to like start viewing like websites in other countries or whatever? And so the idea behind a virtual private network is that, like, let's think back to the company example for a minute. Where's the company example? Where are you? You are, okay, maybe not. Okay, here, you're the company example. So maybe one of these employees like takes their computer and like goes on a business trip, and now they're outside, they're in a different country or whatever. And so maybe now, because they're on the outside, the firewall thinks, oh, you moved outside, you're the attacker now. You cannot make connections to the inside. But the employee is like, but wait a minute, I'm the employee. I was in your network just a moment ago. I just had to like go somewhere else. And so now the firewall thinks you're on the outside, but you want to be on the inside. So like, how do I reconcile that? This is where the virtual private network is going to come in handy. And so the virtual private network is going to create a tunnel. Where is the VPN slide? Okay, the virtual private network is going to create like a tunnel. It's like a secure TLS connection that's going to connect from that employee who's like on business trip on the outside directly through TLS to a connection or to a server that's on the inside. And so now, anytime the server or the person on the outside wants to make a request, they're not going to make the request from their computer outside because the firewall would block that. They're instead going to make the request through the tunnel to the server on the inside. And then the VPN on the inside can now make the request. So now this employee looks like they're still at home in the office, even though they've gone somewhere else. So that's kind of how I think about the VPN. There's this tunnel that allows you to connect inside the network, even though you're outside. So it allows you to pretend like you're inside and bypass the firewall, even though you're outside. And that's kind of the high level idea. This is also why you can use the VPN to pretend you're in a different country, because you tunnel to some server in another country. And then instead of you making the request directly from your country, you're going to use the tunnel and tell someone in that other country to make the request for you. And that's how you make it look like you're from a different country and you download, I don't know, whatever country's Netflix that you're looking for. Okay, so that's kind of a high level idea behind what a VPN is. I think we will also see this again later when we talk more about proxies, but that's one possible idea to get around a firewall, like legitimately, if you're trying to get around it. Okay, so to quickly wrap up, let's talk about what's good and what's bad about a firewall. So here are some things I like about firewalls. One of them is that as the person managing this gigantic network, it allows you a centralized and scalable way to manage your network. So if you're the person trying to like secure this entire gigantic company with like 10 different buildings and whatever, right? All you have to do is build a firewall and make sure that everyone goes through the firewall before they like send their packets to the rest of the world. And now you've secured the entire network with a single machine. That's pretty cool. And say you want to change the policy, like the boss comes and says, we got to be more secure. Or the boss says, all the users are complaining, make it less secure so they can, use their software or whatever. Well, now all you have to do is change the firewall. You don't have to like go around and change every single computer. So that's kind of nice, gives you a single point of control. It can be transparent depending on how you operate it. So now everybody who's using your network, they know, here's the firewall. Here are the rules that it's obeying. So whenever I send connections, I got to follow those rules. So you can make it transparent if you choose to. So that's kind of cool. And then again, you can mitigate security vulnerabilities at the end host. So again, you can have like millions of computers, but they can all be secured by a single firewall, which I find pretty cool. Okay, what's so bad about it? Well, one problem is not all applications work well. So sometimes the firewall is going to, like we said, accidentally block something that it shouldn't block. Maybe the network itself is slower because now the firewall has to check stuff. And so there's one really big problem, which is, remember how we assumed in our threat model that everything on the outside is like bad and evil and scary, and everything on the inside is secure and trusted? But like, who said that's true? What if your threat model is just slightly different and you think that actually the insiders could also be vulnerable or attackers? So now this threat model makes the firewall model totally out the window. You have to come up with something different, because think about the employees on the inside. We assume they were trustworthy, but like, what if they're not? What if the employees can be bribed? Maybe someone like threatens them. Like, that would be super scary. Maybe people take devices from the outside, like their cell phone, and bring it inside the network. And now it's connected to the inside network and it's trusted, even if it shouldn't be. And so it's really dangerous. And if an attacker manages to compromise a computer that's inside, then things could be really bad. Because if I look at my picture, I should really just take this picture and copy paste it everywhere, huh? Okay, so if I look at my picture, imagine if an attacker takes over one of these computers, like, I don't know, this one at the top is like compromised, right? Or is it compromised? Well, then what happens? Now the attacker can send malicious packets to anybody else inside, and the firewall would not know any better because all of this is happening on one side of the firewall. So the firewall cannot see that the attacker is already inside the network and sending a bunch of bad stuff around. So it can be really tricky. We have to be really careful. If we believe that people on the inside are part of our threat model, we could have multiple firewalls. we could start to think about how we would secure individual devices, but it gets more complicated from there. So we're just scratching the surface, but that's kind of the high level idea behind firewalls. Anything else you'd like to know before I summarize? Think of some way to waste 5 more minutes of your time, and then we can all go home. Okay, so here's your summary. Again, today was kind of two different halves, two separate topics. So first we talked about denial of service, and we said there's a new property in town that we care about, and it's the idea that legitimate users should be able to access my service. We talked about two different places you can attack things. You could attack things at the application level. This is the program running at the highest level above all the network protocols. Remember, I could crash the program, like run some SQL injection, delete the database or something, or I could try to exhaust the resources by going after some bottleneck. Different ways to do this include the algorithmic complexity attack, where I force inputs that cause worst case runtime. How do I defend against this stuff? I can use quotas, give everyone a limited amount of resources. I can use proof of work, make the attacker's job more expensive, so now they cannot go ahead and just like exploit asymmetry against me. And then the other class of denial of service attacks is at the network level. Here I'm trying to attack network protocols like TCP or IP. And so here I'm trying to flood the network bandwidth. How can I do this? I could use distributed DOS. And this means I have to get multiple computers under my control, and then everybody floods the network at the same time. And now it's really hard to tell where the packets are coming from. I could use amplification, like the DNS amplification attack, where I spoof a really small packet, and then the strong, powerful DNS server fires a gigantic packet back at the victim. And so I had to spend a little bit of work as the attacker. The DNS server does all the hard work for me, and the victim gets flooded with a gigantic amount of data. To stop this, I can use packet filters, but packet filters, we have to be really careful with them because they could be overwhelmed as well. And also, it could be hard to tell which packets are good and which packets are not. Like if you're using distributed denial of service, how do you tell which packets are good? It's kind of an open question. How do you stop these things? One defense that always works, although it might cost you money, is to over provision, just get a ton of resources and you're good. And we saw using content delivery networks, you could like pay into an insurance scheme to get over provisioning if you don't want to pay for it all yourself. Or you can pay for it all yourself, depends on your threat model. The one example of DOS that we really showed in detail was SYN flooding. And here the idea was that if an attacker sends a ton of SYN packets over and over and over again, then that's going to cause the server to allocate a ton of space because every SYN packet represents a new connection. The TCP or the server receives it, says, oh, time for a new TCP connection, allocates some memory, and that's going to cause the server to exhaust tons of space. But crucially, the attacker doesn't have to remember any of this stuff because the attacker is just sending a bunch of SYN packets and forgetting about them right after. So the attacker spends zero memory, the server spends tons and tons of memory. There's asymmetry there. The way that you stop it is to use SYN cookies. And here the idea is when the server receives a SYN packet, it's not going to store state right away. It's going to say, I'm going to hold on to this. I'm going to fire it back at you, the client, make you remember it and give it back to me when you truly want to finish this connection. So now if someone's just flooding a bunch of SYN packets, they're no longer going to cause the server to exhaust a bunch of resources because now the server is making the client go first. Okay, and then the final thing we talked about was firewalls. The idea was that if we have a threat model, which is not a totally accurate one all the time, that everyone inside my network is trustworthy, I want to protect them. Everyone outside my network is bad and evil, and I want to keep them out. Then I can use a firewall to separate everyone. It's a single source of like mediation where everyone incoming and outgoing has to go through the firewall. And then from there, all I have to do is define a policy, a set of rules that says, when a packet shows up, do I choose to accept or do I choose to reject? How do I do that? I could just look at every packet one by one. That would be stateless. I could look at packets together and think about connections that would be stateful. But we already saw that you can like reorder packets. You can split the bad words, the magic words across different packets. You could exploit time to live and do all sorts of really fancy things to avoid getting detected by the packet filters. But these things sometimes have to be really sophisticated to find the things that it's trying to look for. And then the final thing I talked about was the idea behind proxy firewalls. And so here the idea is I'm not going to look at every packet one by one or try to reassemble the connections. I'm going to say, don't just make a connection inside and then I have to piece it together myself. Actually, make a connection to me directly as the firewall. And then if I think this connection is good, I will make a separate second connection with the end host that will forward all of your messages for you. Okay. Anything else you want to know? I guess it is 6:29, so I don't really have anything else to say. Anything on Zoom that I missed? Okay, cool. So hopefully project 3 is coming along okay. If you're still working on project 2, hopefully you're almost there. We're around if you want to talk about it or if you need help. But okay, besides that, see you on Wednesday for more networking potpourri. Bye.